Now we'll see gate problems related to memory architecture. The question number 1, which is asked in GATE 2015, assume that for a certain processor, a read request takes 50 nanoseconds. Let us imagine that this is your processor, okay? So whenever you request a read, then it takes 50 nanoseconds. But when on a cache miss, okay, there is a cache, sometimes there is a miss, right? So when cache miss, there is a penalty, and there is a chance that cache might hit. So there are two cases. We have to see what happens in each case. 50 nanoseconds on a cache miss and 5 nanoseconds on a cache hit. That means the processor takes 50 nanoseconds whenever there is a cache miss and 5 nanoseconds to get the data whenever there is a cache hit. Suppose while running a program, it was observed that 80% of the processor's requests result in a cache hit. So what is observed? 80% of the time there is a cache hit. Now the question is the average read access time in nanoseconds. He has given everything about readings, right? Now we have to find out average read access time. So if you see, in 80% of the time we will be hitting the cache, only 20% of the time we will be missing the cache. Let me divide the problem into two cases. So here remember one thing, they have not given you cache access time at any time, correct? So they have not mentioned anything about cache access time and main memory access time, right? So they have given complete process. You don't worry about that cache access time and main memory access time. They have given the values in a different way. Whenever there is a cache hit, then to get the data it takes just 5 nanosecond. Whenever there is a cache miss, so what that processor will do doesn't matter for us, but end of the day we will be having penalty 50 nanosecond. Now the problem is very simple. To find out the average access time, we have to divide all the cases into two parts, right? Now see, all case number 1, case number 2. Case number 1 is nothing but cache hit. Case number 2 is cache miss. So the probability of hitting the cache is 80%, correct? So 80% of the time, what is the penalty? 20% of the time, what is the penalty? If you find out, then you get average access time, isn't it? This is the formula. 80% of the time read penalty plus 20% of the time read penalty is nothing but total average read penalty. We will see. So 80% of the time we will be investing only how much time? Because clearly mentioned 5 nanoseconds, and 20% of the time we are only investing 50 nanoseconds. Some students will have this doubt, sir, 20% of the time we have to invest 50 nanoseconds plus 5 nanosecond. That is wrong, because this 50 nanosecond plus 5 nanosecond formula, when you assume this 50 nanosecond as main memory access time and 5 nanosecond as cache access time, but this 50 nanosecond and 5 nanoseconds are not explicitly cache access time and main memory access time. This entire 50 nanosecond might be, because they have clearly mentioned that this 50 nanosecond is the total amount required to fetch the data when there is a cache miss. That's why, so we don't require to do anything else, simply take 80% of the time 5 nanosecond, 20% of the time 50 nanosecond, right? So then you don't require to apply that process. Then 80% into 5 nanosecond, what is that? If you simplify, it would be 400 nanoseconds plus 20 into 50, 1000 nanoseconds by 100. Then I can cancel like this, 2 zeros here, 2 zeros here. It would be 10 plus 4, 14. So 14 nanosecond is the final answer, right? So here don't apply that formula, because that formula is not applicable here, correct? Because they did not give you cache access time and main memory access time. If they give cache access time, main memory access time, then probably we can go for that formula. That's it. See this question. A computer has an L1 cache, an L2 cache and a main memory unit connected as shown below. See the picture. Main memory and cache are connected using a data bus of size 4 words. Remember it. Now between L2 cache and L1 cache we have a data bus of size 4 words again. Okay, remember it. Now the block size in L2 cache is 16 words. That means in a cache, in this cache we know that we will have blocks, right? The block size is 16 words. You know one thing, whenever we transfer the data from main memory to cache, then we have to transfer 16 words. That is what, the intention of fixing the block size, right? Now, the memory access times, and one more thing, the block size in L1 cache is 4 words. That means L1 allows only block size 4 words. That means whenever we transfer data from L2 to L1, then it allows only 4 words, right? Because here maybe the spatial locality is fixed to 4 words, okay? Now what we are going to do is, the memory access times are given 2 nanoseconds, 20 nanoseconds and 200 nanoseconds. 2 nanoseconds, 20, 200, right? Now for L1 cache, L2 cache and main memory. Now when there is a miss in L1 cache, when there is a miss in L1 cache and L2 cache, that means there is a miss here and here, then what are we doing? So he is clearly explaining you what to do. Follow it. First, a block is transferred from main memory to L2 cache. First, a block is transferred from main memory to L2 cache. Fine. Then after that, one block is transferred from L2 cache to L1 cache. Fine. One block is transferred from L2 cache to L1 cache. What is the total time taken for these transfers? There are 2 transfers, and how much time they will take. So we have to answer this question. It's a mathematical question, right? You understand the concept. When it comes to implementations, there can be multiple implementations, okay? So because in this question they have specifically said that we have to move the data from here to here and here to here, you blindly follow it, okay? First, we have to move the data from here to here. Already I told you the data transfers are block transfers, but block size is 16 words, but at a time only 4 words can be transferred. And main memory access time is 200 nanosecond for what? 4 words of data. So that is what may be assumption, right? If you assume that for every 1 word it takes 200, let's assume like this, for every 1 word if it takes 200, let us say, then to transfer 16 words, 200 into 16, 3200 nanosecond. There is no such option, right? Then definitely I can say that. So the data main memory access time 200 nanosecond is for transferring 4 words, okay? 1 block transfer. If that is the case, we are going to, because the width of the database is only 4 words, then we have to move 4 words 4 times. Then main memory will be accessed how many times? We will see here, okay? I am writing here. So you will be accessing main memory 4 times because there are 4 blocks to be transferred, right? Sorry, 16 words to be transferred, 4 words at a time. Then main memory is accessed 4 times, 200 into 4, 800 nanoseconds. Now each such word should be moved to cache, right? So here generally that whenever you are accessing main memory, then parallelly we will keep that in cache. Then generally cache access time need not be counted, but actually options won't match. That's why what I'm doing is, so I am assuming that, let's say you take one 4 word set of 4 words and from main memory and transfer that to cache. In that way I am dividing the work into 2 parts. Take the data from main memory, it takes 800 nanosecond, 200 for each. Then every such 4 words you keep in the cache. Further you have to access the cache, okay? Then each access takes 20 nanosecond, then 20 into 4 times, 24 is 80. Finally, to simply transfer the data from here to here, how much time it took? 880 nanoseconds, okay? Next, we have to do the same thing here to here, but here we have to only transfer 1 block again, because L2 to L1 also we have to transfer only 1 block. That is clearly mentioned in the question. But block size is 4 words and the data bus size 4 words, then only 1 time transfer, right? Access L2 cache, take the data and keep it in L1 cache. For that, access L1 cache. So we have to access L2 cache and L1 cache. If I access L2 cache, then how much time it will take? 20 nanosecond, correct? 20 nanoseconds for accessing L2 cache and accessing L1 cache 2 nanoseconds plus 2 nanosecond. So it would be 20 plus 2, 22 nanoseconds and 80. If you sum it up, you get 80 and 22. It would be 2 here, 8 plus 2, 10, 1 plus 8, 9. 9 not 2 nanoseconds. So here we are transferring 16 words, 4 at a time. Here we are only transferring 4 words because The transfer depends on L1 cache here. That means, I can say left side cache. Whenever you are transferring data from L2 cache to L1 cache, this question arises. Sir, should I follow the block size of L2 or block size of L1? Simple. Who is requesting that block? Here L1 is requesting the block, right? That means L1 wants to have some block. Obviously, we have to depend on this L1's block size, not L2's block size, right? L2's block size is defined for transfers between main memory to L2 cache, right? Because L2 is at requesting side. So remember one thing, generally when you have different sizes of blocks, then when the transfer occurs, then the size of the transfer depends on the requesting component. Here in L1 cache and L2 cache, when you are transferring the data, requesting component is L1. Similarly, between main memory to L2, we can assume that L2 is the requesting component. That's why it would be here to here 880 plus here only one block size is 4 words and we are transferring 4 words. That's why 20 into 4, 80. This, not 20 into 4, only 20, because to transfer 4 words it takes only one memory access time, 20 nanosecond, and to transfer the data to here only one time, it is one memory access time, 2 nanosecond, 20 plus 2. Okay, but why I took 200 into 4 here? Because we are transferring 16 words, 4 words at a time, so 4 times we have to do. That's why 200 into 4 here and 20 into 4 here in the first component. That's why 880. Understand? So 902 is the answer. In that way, so by seeing the options, we can answer this question. If you have, sometimes students say, sir, I got different answer. My model is like this. What is that? Sir, whenever I am transferring the data, then I access main memory. At the same time, this cache is also accessed, correct? Because you are doing parallelly. That means you are transferring the data from here to here. Then why we have to take the access time of cache? That access time of cache will be cancelled by this main memory access time, correct? Example, let's say you are transferring data from some x to y, let's say, okay? Then x takes 1 hour to take the data, y takes 1 hour to take the data. Then why we require 2 hours? Because we can do parallelly. While taking the data, we are taking the data and sending the data at a time. Then maybe only 1 hour we can consider. If that is your idea, then answer supposed to be, see, like this. Simply I take the data. To take the data, it takes 200 nanosecond, right? So 200 nanosecond is to access the data, right? And at the same, to access the data and to send the data also. If you assume like that, then probably it would be 200 into 4. You are accessing and sending the data to here. So 200 into 4. Then after that, here to here, you access here and send it. And let's say neglect this L1's access time, because whenever you are accessing L2, at the same time you are also accessing L1 for, right? So I can say that at that time 20 into 1, it would be 820, correct? But there is no 820 here. That means, so the examiner is not thinking in that way, right? So maybe examiner is thinking in this way, like how while accessing main memory, don't consider accessing cache. Access the main memory, then store the data into L2 separately. That's why we have to count that also. Okay, it depends on the question, that's it. Okay, otherwise, I can say this question is not well framed. There is no fixed answer, right? But what we did is, because we understood the examiner and we, by seeing the options, we explored all possibilities, and I have realized that maybe this is the idea examiner is thinking. That's it. Okay, we'll see this problem, which is asked in GATE 2004. Consider a system with 2 level cache. Access times of level 1 cache, level 2 cache and main memory are 1 nanosecond, 10 nanosecond, 500 nanosecond. So we have 2 levels of caches, L1 and L2, and 1 main memory, right? So that is what mentioned in the question. The access times are 1 nanosecond, 10 nanoseconds and 500 nanoseconds. The hit rates of level 1, level 2 caches are 0.8 and 0.9. 0.8, 0.9. So 0.8 also can be written as 80 by 100 and 0.9 can be written as 90 by 100. What is the average access time ignoring the search time within the cache? If I ignore the search time, so don't worry about this statement. What he is saying is, whenever the cache is associative cache, what we do? Otherwise set associative cache. Then once we find out the right set, then within that set we will be searching for the block, because the block can be, example, it is 2 set associative mapping. Then we will be searching for this entire set, correct, for the block. Maybe block 1, block 2, everything will be searched. If it is associative, then every block of the cache will be searched, right? And that entire thing is part of the cache access time, right? We say that entire thing is cache access time. So already cache access times are given, then we never bother about search time within the cache, because that's a part of it. So however we'll be ignoring it, but he mentioned that ignore the search time. We never consider it. Now what is the average access time is a question. It's a straightforward question. We have a formula, right? We have to apply that formula. We know that every time we access L1, whenever there is a miss in the cache L1, then sometimes we access L2 and main memory, sometimes only we access L2, correct? So when you access only L2, when this cache hits, when you are going to access main memory, when L1 miss, L2 miss. Now you see, L1 is always accessed. Now whenever there is a miss in the L1 cache, then L2 is always accessed, but main memory is not accessed always. When L1 is missed and L2 is missed, then main memory is accessed. Okay, we express this as a formula. So average memory access time, if you want to know, then 1 nanosecond penalty is always possible, plus sometimes what happens, we will come to L2, right? When L1 misses, right? What is the miss percentage? 0.8 is hit, then 0.2, correct? Let me write it as 20%. 20% of the time what happens is, we miss in L1, then we'll come to L2, then definitely we access L2. So what if L2 doesn't contain data? Then also we access it. How? Because we are going to main memory and we are transferring the data to L2 and we are accessing it. So I can say that always we access L2 cache in this 20% of the time, but we don't access main memory always in this 20% of the time. In this 20% of the time, if L2 also misses, what is the percentage of time L2 misses? 10% of the time. That means in this 20% of the time, 10% of the time we miss L2 cache, then we'll come to main memory, that is 500 nanosecond. This is a formula. Okay. Let us simplify it. It would be 1 nanosecond, because all are nanoseconds. Let me write just values. 1 plus 20 by 100 into, I am multiplying this and this, into 10, plus 20 by 100 into 10 by 100 into 500 nanosecond. Okay. If you simplify it, 0, 0, 0, 0 cancelled. Then 1 plus 2 plus, here you see 0, 0, 0, 0, 1, 2, 3, 4 zeros on top, 4 zeros on bottom. Then it would be 2 5s are 10, right? So 10 plus 2 plus 1, it would be 13. 13 nanosecond is the answer. Okay. So in that way we can solve questions related to average memory access time. Okay.